Yes, okay. My motivation to do carbon dioxide removal. This is me 2018 on the Polarstern, the German icebreaker. We did research in Antarctica, and my colleagues measured the temperature of the ocean in Antarctica over many years, and they told me it's getting warmer. Antarctica is the most stable ice sheet in the world, and it starts melting from the bottom at a global warming of only 1.1 degree. Even if we stay below 2 degrees, it will continue over centuries and millennia. It will displace half or more of humanity because of sea level rise. So we have already caused irreversible changes also in many other parts of the world, like corals, permafrost. The Swiss glacier will disappear very likely, and the Rhine someday will also disappear, maybe in summer, but also, yeah, I don't know if in winter too, but even if we solve the climate crisis, we have damages that we cannot reverse. And it's very hard to see, it's very heartbreaking to see this when you're doing research on a research vessel, because we emit lots of carbon dioxide and our results do not change the policy. We don't contribute to a better future. And so I said, to be able to look in the mirror again, fuck that shit. I'm doing CDR and I'm very serious about it. Okay, let's talk about PyMiCCS back on land. Obviously, we have the syllables PyMiCCS. So CCS is standing for carbon capture and storage. You know it already. Pi is pyrogenic carbon. Through pyrolysis, we create stable organic carbon. I cannot tell you anything more about biochar. You know it better than me. We want to use it for soil improvement, and we also want to take the mineral weathering into account. Weathering is a process where minerals, water, and carbon dioxide react with each other, and through weathering, we create bicarbonate out of CO2. Bicarbonate is harmless. You can drink it, I prove it. So when you look at the chemical analysis on your water, you find something called hydrogen carbonate. Hydrogen carbonate is bicarbonate. In chemistry, we have many names for the same stuff, just to torture you. You can see we don't need photosynthesis for this. So this is weathering is occurring on Earth since 4 billion years, so even before there was life on Earth. And today it removes 3% of our carbon dioxide emissions every year for free. You don't know everything about biochar. I don't, maybe nothing about mineral weathering. So my goal is to teach you what this is. I said we turned CO2 into bicarbonate. We, in the laboratory and our scientific papers, we described idealized weathering reactions. Of course, this is nothing what happens in the real world. Because we don't have pure minerals outside, we have rocks. And rocks, most rocks consist of different minerals. They all have very specific chemical composition. They weather all in another way, and it's getting a bit complicated. You can weather a mineral faster when you have a high temperature, a low pH, or a very big surface area. So if you grind down the rocks, you enlarge the surface area in relation to the mass, and you have a faster weathering. And you can enhance the weathering if you put rock dust into soil, because we have a very high CO2 levels in the soil, so 20 to 50 times higher than in our air here. We have microbial and fungi activity. That means more action, more weathering. And we have humidity, because if you just throw stones on the surface, it might fall dry, but inside the soil, we have, the water that we need for the reaction. So let's go under the earth into geology. We work a lot with basalt rock. You might know it. It's in Iceland and Hawaii, and is building these kind of columns. We also have it in Germany, in the Eifel. And rock basalts mainly consist of 3 mineral groups. That's the pyroxene, the plagioclase, and the olivine. Don't remember the names, it's not important. You just have to know we have a lot of different minerals called augite, enstatite, albite, forsterite, and so on. And this is our green superstar, so I will explain you how this is weathering. Now, I made very bad experience in chemistry lessons in school. Maybe you can relate to this. And so I was searching for a simple image, how to explain the chemical reaction of the weathering, like an all-day image we all can relate to. I found some. Chemistry is like swapping partners. So imagine during the pandemic, we were at home, we were very bored, and now we're free again to go out, to go to conference dinners, and we're attracted to other ones. This is what chemistry is. So chemicals or atoms are attracted to other atoms and they start swapping. So we're in Darmstadt. Imagine Saturday night in Darmstadt, an olivine mineral is going to a bar and going on the dance floor. It meets 4 molecules of water and 4 of carbon dioxide. They drink a lot of apple wine. And it happens that magnesium becomes single because silicate is attracted to hydrogen, and also water and carbon dioxide. They want to try something new and form bicarbonate. I see you can relate to this. You know the situation. So you also know that at the end of the evening, the DJ plays some Barry White. So magnesium is getting romantic and asks carbon and oxygen, do you want to live together with me? And they say, oh my God, yes. They're so excited. They form magnesite. And magnesite is a love that will last many thousands of years. Silicate decides, okay, we also want to settle down, and water and carbon dioxide go to the next bar to weather another mineral. So relationships can be very complicated also in chemistry. What you shall remember is the pathway of carbon dioxide. So in the first step of the reaction, we transfer the carbon dioxide completely into bicarbonate, which you can drink. And then the second step, some of the carbon dioxide is released, half of it, and the other half is going into a solid phase. So the carbon dioxide we have released by burning fossil fuels is going back to the geological cycle. So very long time. What comes next? So this is the idealized weathering reaction. In the real world, we have lots of different minerals. They are weathered. Then we have lots of different free cations. You see, we have very delicious magnesium, calcium, potassium. So the plants in the soil are very happy about that, that we're weathering the rocks there. This is also promoting clay formation in the soil, and the bicarbonate is mostly transported to the ocean. It will travel for a long time via the groundwater flow. And in the ocean, it can remain about 100,000 years in the water body. And if we have the formation of a mineral, it's mostly calcium carbonate because mussels and corals and algae, they form their shells out of it. So we know that biochar has a lot of positive impacts on soil. We also know this from mineral weathering. So we have a slow nutrient supply. We increase the pH by catching the carbon dioxide. We have clay formation. In consequence of that, we have a soil organic carbon stabilization, and we have a very long-term carbon storage, so 100,000 years. I'm sorry to say this, but this beats biochar. Mostly. People are thinking like, okay, why don't we mix it together? And I heard from many of you that you already mix rock powder and biochar together. And the other idea is to co-pyrolyze it. So put rock powder together with a biomass, it's like doping it with compost, but we do it with the rock powder. And the big question now is, so what can we, so what are the results? do we create a product or a material which can do much more than these both together. So our project started 3 weeks ago. We don't have any results. Don't ask me about this, please. But there are some pre-studies about, for example, the co-deployment of pyrogenic carbon and mineral powder. My colleagues did an assessment. They said, okay, if we mix biochar and enhanced weathering and put it also in relation with afforestation and BECCS, we can have some synergy effects. For example, we have a bigger nutrient pool. We also have the nutrient retention. Both is leading to a higher growth of biomass. Then we get an optimization of the soil hydrology. And my colleague also published this year is another study that enhanced mineral water interaction is leading to a faster weathering. So if the biochar creates or increases the water holding capacity of the soil, the weathering is benefiting from it. Then we also have an increase of the soil pH. Biochar is leading to a higher mass of soil biota. Biota action is good for weathering. And if we use rock powder, which contains trace metals, at the moment we use a basalt powder, which is within the European guidelines for fertilizers, but we could also use other rocks if we know that the biochar would bind our trace metals that are released. There's one more thing. You can see that if you have a lot of minerals in the soil, there is a calcium coating forming around the biochar. The cracks in the biochar can be filled and sealed by small particles. We have that negative priming, which Claudia also mentioned yesterday. And you can see on this photo here, it's biochar, and this is a pore in biochar. And here, minerals are sitting in the pore and clogging it. And yeah, there was a study, or several studies showed that you can have an up to 50% reduced carbon loss of the biochar if you just mix it together. That was the mixing or co-deployment. Now we're talking about the doping. So the idea is to dope biomass. You can spray a fertilizer on it. You can soak the biomass in something, or well, like we do, we add dry powder and we pyrolyze it together. And there are also some studies on the market outside that show an increased stability or reduced degradation and an increased nutrient availability. So let's talk about the stability. There is a very, very good review paper from Bus et al. From this year, and they made a review of all what is available outside, and they said, like, okay, if we compare the doped biochar to the normal biochar, we see the yield of stable carbon is always higher. Then also the total yield of biochar is higher than the normal biochar, and you also added the minerals, so you get more mass from the same amount of biomass. This is also reducing costs. Yeah? And another very good review study also from this year, from NAN, and they were looking, okay, what is chemically happening during the co-pyrolysis? You can have a physical coverage, then you create a lot of new chemical bondings like organometallic bonds, metallic covalent bonds, and so on. So everything increases the stability of the biochar, and you have something like direct air capture in the pyrolysis. When you have the outgassing of carbon dioxide and you have added calcium or magnesium oxide, it immediately forms calcium carbonate. Super cool, I think, yeah. So, and what they observed is that the amorphous carbon is shifting to graphite-like domains more and more. Shame on you. We have an enhanced formation of aromatic, so high aromatic carbon and diminished biodegradation. You know what I mean. Yeah, so that was the stability. The nutrient availability is also very, very important. And this reminds me of the bone meal or the slaughter waste we had yesterday. So if you take a feedstock which is rich in phosphorus and you dope it with potassium, you create potassium phosphates. They are very good or highly soluble in the soil, and the plants can reach it very well. So you create a PK fertilizer and a more stable biochar. If you have a phosphorus poor feedstock, you can also dope it with different substances, and you create also such kind of fertilizer. And the big question is like, if we add something like mineral powder, where we don't have K or P, which is available during pyrolysis, what happens there? We don't know. Good that we're studying this. And so this is our goal in PyMiCCS. Now we're coming to PyMiCCS. We have a 3-year plan to study what happens if we mix straw, wood, and cocoa shell, so a phosphorus poor biomass with basalt powder called Eiffel gold. You know, all know Eiffel gold, I know this. We co-pyrolysis it, but we also co-deploy it. We will do a lot of experiments, making our hands dirty in the lab, but also in the greenhouses and fields. We put all this information into models to see what are the ecosystem consequences for this. Is this economically feasible? One of the review papers said always when you co-pyrolyze or if you dope your biochar with something, you always get a lower cost. And we want to transfer this knowledge to the industry and to farmers, and also shared with our project partners in CDRterra. So coming to an end, we have 2 strategies to mix them, so doping and co-deployment. We expect a lot of positive outcomes from this, and but while we reduce the degradation of biochar and also the costs of the material. And there's also one very nice point. This is we can create a complementary CDR portfolio with this. We had a very lively discussion about the stability of biochar yesterday at the dinner. So if you put biochar in the soil, it degrades. And it loses carbon over time. If we put mineral powder in the soil, it starts catching carbon, and it starts a bit fast, but over time it slows down. So if you look at they equalize each other, and you can create something like a stable amount of carbon storage by co-deploying them too. We're not sure about the details, like how fast is the weathering process going on and how fast is the biochar degrading, but they are equalizing each other. So this could be interesting for the future carbon market. We expect increased CDR potential because we're looking like, okay, we have the CDR potential from pyogenic carbon, from mineral weathering plus X, because we will likely create co-benefits like a stabilized biochar. We will also stabilize the soil organic carbon. We will enhance the weathering, so have a faster uptake of carbon dioxide, and increase plant growth and health, which raises the question, okay, why shouldn't we mix it with BECCS and afforestation? Last slide. So thank you for your attention. Please subscribe to our newsletter from CDRterra. You also find us on LinkedIn and Twitter. You also find me on LinkedIn and Twitter. I have 3 recommendations of literature. I can also give it to you if you contact me. If you want more enhanced weathering entertainment, just go on YouTube and look for my science stem called Das ist keine Lösung, or get your link here. And you're thinking of biochar day and night, that's nice, but please also consider mineral weathering, because I think this will be a very hot topic in future. Thank you very much.
Toll. Vielen Dank für diese spannenden Inhalte und dass du ein Lächeln
Thank you so much for these exciting insights and for making us all smile. Are there questions from the audience?
alle überlegen sich noch, wie war das?
Yeah.
mit der Partnerwahl.
Everybody is considering, you know, what was the bar and the partners, and you know, everybody's flashed and overwhelmed by this great presentation. You opened a new area to be minerals, to add minerals that should turn into a standard.
Pflanzen verfügbar. Also, Calcium.
Is it calcium that is not so much plant available with phosphorus, or is it magnesium or the kalium that is soluble again? I did not really get it. What is appetite and what is plant available? Should I answer in English or in German?
About the solubility of apatite and phosphates and potassium.
Ja, Sie haben gesagt, das sei sehr stark pflanzenverfügbar.
You said that it's highly available for plants if you use substrates rich in phosphate and mix it with the minerals.
But it depends on what kind of phosphate you create. Is it potassium phosphate or calcium phosphate? The solubility of this mineral is different, and the potassium phosphates are very good soluble. And I think I remember that calcium and magnesium phosphates are not so soluble. So yeah, it's really depends on the chemical composition of this mineral. And that was very outstanding that you they took bone meal and put some potassium on it, and then they had, instead of a 2% availability, they had a 10% availability of phosphorus or so. Yeah, but I give you the paper for more details.
Sehr charmanten Vortrag, wirklich großartig.
That was a very charming presentation. Thank you so much. It was great. Do you cooperate also, this is my question, with scientists analyzing soil life in order to understand how bacteria, fungi, and small animals accumulate or multiply in the soil or whatever?
We cooperate with soil biologists. We have soil scientists involved. They mainly look at the chemical and physical properties of the soil, like clay formation and cation exchange capacity. And for biota, I think we don't have anybody in our project, but we know that, for example, fungi increase the mineral weathering because they bound or they are very hungry on iron and magnesium, and so they can enhance the weathering with this. I don't think we have biologists with us right now, but we hope to get an extension after the 3 years, and then in future, yeah.
Afforestation on your, let's say, schedule. So this would be very important. And
and we know that the biochar increases the mass of soil biota and for minerals. I'm not sure if we have studies on this, but
yeah, Claudia has a question, but maybe first to online and then to Claudia.
Thank you very much. Really nice feedback for your presentation here in the chat as well. Carol Schwald is interested in the question, if pores are filled with the minerals, don't we lose the filter attributes and water storage characteristics, for example?
I don't know. We will see. I haven't read anything about that. Clogging the pores is, influencing the well, yeah, it stops the degradation, but I don't know if it stops the water holding capacity of the biochar. So I don't know. But yeah, that's an interesting point to look at.
Yeah, I wanted to just supplement what you said, because we are going to include studies on C13 pulse labeling, which means that we will, under controlled conditions, label the carbon that enters the system by the plant, fixed by the plant and given to the below ground soil biota. So there will probably not be direct studies of the microbial communities or even there will be, if I can get my colleagues on board who are interested in that, but we will have a chance to see how much of the carbon that is transferred below ground goes to different compartments of the soil, of the soil system. So into aggregates, into microbial biomass and so on. So I can't tell yet how deep we can go there, but you know, as deep as time and money allows in that regard. I think the pore clogging will probably reduce some of the capability of biochar to do sorption to other compounds. But this is what, if you would use a new dose of the biochar mineral mixture each year, like being part of a fertilizer, like we discussed yesterday, I guess you will always add a fresh capability to sorb other compounds, and over time it will get into this coating and reduce the capability of the biochar to be degraded in that way. So, like you said, we will see. It's what research is for.
Online that you
Maybe one short question from Andreas Hellmann. What do you think with already rich material feedstock like rice husk? Is there any possibility to substitute some of the olivine?
With rice husk? Well, that's organic, but I don't understand.
The mineral content in those rice husks. Do you expect any interaction?
There's always interaction. But I think the advantage to add minerals, so inorganic minerals or inorganic bound minerals, is that we can form organic, non-organic chemical bonds, and like clay or organic complexes can also increase the stability. And I think we the big advantage is that we have inorganic and organic compounds merging together. You can also add rice husk, but I think then you're doping organic with organic, and our goal is to dope organic with inorganic. So I don't know how expensive your feedstocks are normally, but a ton of basalt powder is between 35 and 70 euro per ton. So I didn't make any calculation, but in the one review paper, they said they calculated all the process and took into account that you create a higher amount of biomass, and they always said like, okay, it's equal or even lower costs for a doping than without doping.